Hello, and welcome to the 12th lesson of the Big Data and Hadoop Administrator course offered by Simplilearn. In this lesson, we will discuss Hadoop Security. After completing this lesson, you will be able to describe the different ways to avoid risks and secure data, identify the different threat categories, describe the security aspects for different nodes, describe operating system security, describe Kerberos and how it works, describe service-level authorization. In the first topic of this lesson, you will learn about the security models pertaining to information security, categories of threat, and how to assess potential threats with regard to security of systems or cluster. Hadoop ecosystem and its components, along with processing frameworks, allow you to store data and process it in new and exciting ways. This allows different verticals to use the same technology paradigm in various use cases. However, this raises a concern about how to avoid the following risks associated with managing massive volumes of data in a cluster: privacy violations, regulatory infractions, damage of corporate image and shareholder value, data integrity compromise, damage to business continuity plans, time and financial loss. The solution is implementing security. Let's understand in detail the different ways to avoid, categorize, and assess risks and secure data. One of the main information security models is the CIA model. It stands for Confidentiality, Integrity, and Availability. These are also the three components of the model. The three components of the model can be applied to a wide range of information systems. They help the CIA model to organize information security. The CIA model is not a strict set of rules. However, one should be aware that the security features in the Hadoop platform may span over more than one CIA component, or none at all. Let's understand the components of the CIA model in detail in the following screens. Confidentiality is a security principle that emphasizes the notion that information should only be seen by the intended or authorized recipients. Confidentiality is established by using a unique identity or identification method that allows data access to specific personnel. This happens through authentication, thus making identity and authentication key pillars of Hadoop security. Encryption, though not mandatory, is an important concept of confidentiality. It is a mechanism of applying mathematical algorithms to mask data or information. This ensures data safety even if it lands in the wrong hands. Encryption is a process of locking data in a format that can be read only if unlocked with the correct key. Encryption ensures data safety and keeps its confidentiality intact. Integrity is an important component of information or data security. It ensures that information remains unchanged and uncompromised, irrespective of whether it stays in one place or travels from one point to another. Unlike the previous two components, availability is about preparedness. Availability of data or services can be impacted by regular outages, implementation of security patches, or security events like denial of service attacks. The triple A's are authentication, authorization, and accounting. These are critical for secure computing. Let's understand these components in detail. Triple A's refer to an architectural pattern in computer security, where users of a service, data, information, or platform prove their identity, are granted access based on predefined rules and policies, maintain a record of user actions for auditing purposes. Closely tied to AAAs is a component of the CIA model: identity. Identity and identification method refers to the process in the system that distinguishes between different entities, users, and services, and allows or disallows the user to access the data. The 5 pillars of enterprise security are administration, authentication, authorization, audit, and data protection. Security administrators must provide enterprise-grade coverage across each of these pillars when they design the infrastructure to secure data in Hadoop. If any of these pillars remain weak, it may result in damages and associated risks. Let's learn about the importance of securing distributed systems. No business can afford to have big data insight come at the expense of enterprise security. Potential threats and complexity involved in implementing security measures are directly proportional to the magnitude of the system being distributed and increase as distributed systems scale. To arrive at a robust security architecture for a distributed system, it is important to understand the probable and potential threats and to categorize them to better understand what security mechanisms need to be in place to help mitigate or avoid those threats. Earlier, everyday banking meant driving to the local bank, visiting a bank teller, and conducting transactions in person. The bank's security measures would have included checking the person's identification and account number and verifying that the requested action could be performed. Over the years, banks became larger. The local hometown bank probably became a branch of a larger bank, thus giving you the ability to conduct banking not just at the nearby location, but also at any of the other locations. The security measures necessary to protect assets grew because there was no longer just a single physical location to protect. Also, more bank tellers needed to be properly trained. Taking this a step further, banks eventually started using ATMs to allow customers to withdraw money without visiting a branch location. As you might imagine, even more security controls became necessary to protect the bank. Next, banks became interconnected with the other banks, which allowed customers from one bank to use the ATMs of a different bank. Banks then needed to establish security controls between themselves to ensure that no security was lost as a result of this interconnectivity. Lastly, the Internet movement introduced the ability to do online banking through a website and even from mobile devices. This dramatically increased potential threats and the security controls needed. There are 3 threat categories: unauthorized access or masquerade, insider threat, denial of service. Unauthorized access is the most common form of the threat category. A masquerade attack refers to an event when an invalid user presents himself or herself as a valid user by obtaining valid credentials. These attacks can be detected by looking at unsuccessful attempts from audit logs or by profiling login attempts by IP addresses. Insider threat is the single most damaging threat category. Here, the attack comes from a business or from regular users such as employees, contractors, or consultants. These threats arise when an unauthorized user has access to data via some unknown but authorized user. Denial of service is a situation where one or more clients are unable to access a service. The service may be access to data, processing capabilities, or usability of a system. This is detected when requests come from multiple systems in parallel, causing excessive network traffic. This will result in the distributed system denying some valid requests or even a failure of the complete system. In a distributed environment, attacks to distributed multiple systems might not be possible. However, attack to one firewall or network access switch can be of major impact if not protected. Assessing the threats to a distributed system to assess risks requires understanding the users and the environment. Risks of potential threats can be assessed by user assessment, environment assessment, vulnerabilities. User assessment refers to the important process of assessing users who will have direct or indirect access to the distributed system. Users can be classified based on their roles, line of business, and work activities. This helps in identifying their access patterns and usage of tools within the system or access areas like logs, system interfaces, monitoring, or processing points. Environment assessment refers to the critical process of assessing the distributed system and its environment. For example, the environment's access to internet inbound or outbound may lead to the requirement of constant monitoring, alerting, applying software patches, and applying security policies. Understanding location of distributed systems, such as the company, third-party managed data centers, or cloud, helps in risk assessment and risk avoidance or mitigation. Vulnerabilities refer to observing and fixing software or network vulnerabilities by using regular software or network patches. In the second topic of this lesson, you will learn about the security implementation on different types of nodes and operating system security. Each node plays a role in a cluster. Each Hadoop ecosystem component has services, and each service has roles running on different nodes. This takes care of the service's functionality. Here are some examples. Service, HDFS, roles, name node, active, standby, secondary, data node, journal node, failover controller, HTTPFS, NFS gateway. Service, yarn, roles, resource manager, active, standby, node manager, job history server. Service, Hive, roles, Hive Metastore server, Hive Server 2, Web HCAT server. One way to secure a Hadoop cluster is by applying the separation strategy. This involves placing the service roles specifically on separate nodes. The separation strategy involves the following steps. Identify all the master services to be run on master nodes and worker services on worker nodes. Identify which components require client configuration files to be deployed so that users can access the services. These client configuration files, along with client-facing services, are placed on edge nodes. Now, let's learn about the security implementation for different nodes in detail. Master nodes are the most important nodes of the cluster. Therefore, they have a strict security policy to protect them. Due to their importance, only administrators or persons who perform the administrative functions are allowed to access the master nodes. The reason for this limitation are as follows. Avoid any chance of resource contention. Prohibiting users from using master nodes or having access to applications or programs on master nodes decreases the risks of degradation in performance due to resource sharing and contention. Avoid security vulnerabilities. Prohibiting users from using master nodes reduces the chances of exploiting unpatched vulnerabilities in the Hadoop code. Restricting users from having access to master nodes also avoids any risk of security threats to master roles due to user actions. Worker nodes handle the bulk of the functions of a Hadoop cluster. These functions include storing and processing data. It may seem that all cluster users have access to worker nodes. However, access is only provided to the administrators. Users can only work with these nodes through APIs or interfaces. Services provide a proxy mechanism that allows administrators to channel user activity to a certain set of nodes that are different from the actual worker nodes. These proxies communicate with worker nodes on behalf of the user, eliminating the need for direct access. The reasons for this limitation are as follows. Avoids resource contention and skew in resource management that may be a result of regular end users performing activities beyond the expected processes on a worker node. For example, user activity may disrupt or affect Yarn's capability to consume resources as allocated. Avoids worker roles skew in behavior, which may be a result of end users using worker nodes for daily activities. For example, data ingestion from worker nodes may skew disk utilization. Management nodes provide the mechanism to install, configure, monitor, and maintain the Hadoop cluster. Only administrators are allowed to access the management nodes. The management and maintenance of a Hadoop cluster is an administrative function and should be protected. These nodes often contain the actual software repositories for the cluster, especially when the nodes are not connected to the internet. The most critical role hosted on a management node is configuration management software. Whether it is Hadoop specific, such as Cloudera Manager and Apache Ambari, or not, such as Puppet and Chef, this is the place where administrators set up and configure the cluster. Edge nodes host web interfaces, proxies, and client configurations that ultimately provide the mechanism for users to work with Hadoop cluster. Users have direct or remote access to these nodes. The Hadoop ecosystem is inherently complex and needs tools and access methods that are available to allow access to cluster nodes. Examples of such tools and access methods are Firewall and Selinux. Let's understand these in detail. Users' access to specific nodes can be controlled through remote access control tools. Host firewalls can be used to limit the types of traffic going into and out of a node. In Linux systems, host firewalls are typically implemented using IP tables. Configuring IP tables involve knowing about the ports and the IP addresses. Firewall policy can be set to allow any host to reach the allowed ports, or it can be set to allow users to reach and use the specific hosts and ports. The basic name node IP tables policy is as follows. This policy is more relaxed, as it allows all hosts 0.0.0.0/0 to connect to the machine over the common HDFS name node service ports. The policy can be made more restrictive by adding specific IP addresses to the IP tables policy. Selinux, or Security Enhanced Linux, implements security at kernel level and provides Linux kernel enhancements. In a CDH setup, this has to be disabled on every node of the cluster. If disabled, Selinux is not active and does not provide any additional level of security to the operating system. If permissive, Selinux is enabled, but does not protect the system. It only prints warnings when a policy has been violated, and it can be used for workload profiling on a system to begin building a customized policy. If enabled, Selinux protects the system based on the specified Selinux policy. Hadoop ecosystem comprises hundreds of components, tools, and other widgets that integrate and/or enhance the platform in one way or another. As more components and tools are added, it becomes more difficult to come up with a set of Selinux policies to govern them all. If set in permissive mode over a suitable period of time, the warnings generated by Selinux can be used to build a security policy that may become very tedious to manage. In the next screen, let's learn about Kerberos, which is the de facto standard for security implementation in Hadoop clusters. Kerberos is the Greek word for Cerberus, a multi-headed dog that guards the entrance to Hades' world and ensures that those who enter will never leave. Kerberos is a network authentication protocol built on the assumption that network connections are unreliable. Kerberos uses secret key cryptography to enable strong authentication by providing user-to-server authentication. The authentication mechanism was developed at Massachusetts Institute of Technology, MIT. Today, it is one of the most used and relied on security mechanisms to protect Hadoop clusters and prevent unauthorized access to data stored on the clusters. Kerberos is required for the following reasons. By default, Hadoop does not question or verify the identity of the user accessing the cluster. By default, everyone has read access to the cluster and the petabytes of data that it stores. In the case of large clusters, managing access to the cluster at user, group, or data level is not enough to protect it. Someone has to verify the identity of the user or the service before he or it reaches the cluster and its data. Hadoop uses Kerberos as the basis for strong authentication and identity propagation for both users and services. Kerberos is a third-party authentication mechanism in which users and services rely on a third party, the Kerberos server, to authenticate each other. The Kerberos server itself is known as the Key Distribution Center, or KDC. The terminologies associated with Kerberos include the following. Key Distribution Center, or KDC, is the trusted source for authentication in a Kerberos-enabled environment. Kerberos KDC server is the machine or server that serves as the KDC. Kerberos client is any machine in the cluster that authenticates against the KDC. A realm establishes an authentication administration domain. Each realm has its own Kerberos database, which contains the users and services for that particular administrative domain. Principals are the unique entries in the Kerberos database. Each user, host, or service is given a principal. Tickets are issued by the authentication server. Clients present tickets to the application server to demonstrate the authenticity of their identity. Each ticket has an expiry and a renewal time. The Kerberos server has no control over the issued tickets, so even if a user is prevented from obtaining a ticket and he or she already has a valid ticket, then he or she can use it to contact the service until the ticket expires. Key tabs are files that store long-term keys for one or more principals. KDC admin account is an administrative account used to create principals and generate key tabs in the KDC. Kerberos server resides on one physical host. It contains 3 parts: a database of known users and services and their respective Kerberos passwords. These entries are also known as principals. An authentication server, or AS, that performs the initial authentication and issues a ticket granting ticket, or TGT. A ticket granting server, or TGS, that issues subsequent service tickets based on the initial TGT. A user principal requests authentication from the AS. The AS returns a TGT encrypted ticket using the user principal's Kerberos password. It is known only to the user principal and the AS. Cluster resources, such as hosts or services, cannot provide a password each time to decrypt the TGT. They use a special file called a key tab that contains the resource principal's authentication credentials. The set of hosts, users, and services over which the Kerberos server has control is called a realm. If Kerberos is enabled, authentication in a CDH cluster is handled by it. This involves allowing users and services to access the cluster only if they meet the security requirements. Kerberos provides strong security benefits through authentication packets that are unusable by unauthorized users. It also prevents security threats by not releasing access credentials in a readable format over the network. Integration of Kerberos with Active Directory, or AD, or Lightweight Directory Access Protocol, or LDAP, is also possible by allowing options to manage and store credentials in AD. Without Kerberos enabled, Hadoop only verifies if a user and his or her group membership is allowed to access HDFS. There is no other procedure to ensure if the user is who he or she claims to be. With Kerberos enabled, a user must first authenticate himself or herself to a Kerberos KDC to obtain a valid TGT. The TGT is then used by Hadoop services to verify the user's identity. With Kerberos, a user is authenticated on the system he or she is logged into and on the network. Any interaction with other services that have been configured to allow Kerberos authentication for user access is also secured. Cloudera's wizard can be used to implement Kerberos, provided a working KDC is already set up and tested. Enabling Kerberos. In this demo, you will learn how to enable Kerberos. To enable Kerberos for your cluster, you should ensure the following steps are performed. In the Cloudera Manager page, click Administration, then click Security. In the Security page, click Enable Kerberos. When you are enabling Kerberos, the wizard asks you to ensure you have followed the following steps. The first step is set up a working KDC. The second step is KDC should be configured to have non-zero ticket lifetime and renewal lifetime. The third step is that the Open LDAP client libraries should be installed on the Cloud Manager server. And the fourth step is that the Cloudera Manager needs an account that has permissions to create other accounts in the KDC. First, you will need to set up a Kerberos server and a key distribution center, for which you will need packages like krb5-libs, krb5-server, and krb5-workstation. Next, you need to choose one of the machines. In this case, the third machine has been chosen. For this, type su-ec2-user, and then type sshM3. Now the third machine has been set up as a key distribution center. Now, log in as root by typing sudo su, and then type cd. Now you will get the packages by typing in yum install krb5-libs, krb5-server, krb5-workstation. After the packages start getting installed, you need to set the realm name and domain to realm mapping. To do this, type vi/etc/krb5conf, and now you will be able to see the entries within the file. The entries you can see are default, KDC, and admin server. Under the lib-defaults, you can see that the default realm is example.com. Now you will uncomment these values by changing the default realm name to test.com. Now you will define the realms by uncommenting all the entries. Then you will define the host. For this, first identify the host name and provide the new host name. In the Domain Realm section, you need to uncomment the entries by changing it from example.com to test.com. You can see information about the ticket lifetime and renew lifetime. Type WQ to save it. Now you will have to update the KRB5 file with max life and max renewable life entries. For this, type vi/kerberos/krb5kdc/kdc.conf. Under the Realms section, change from example.com to test.com. Now you need to add the max life and max renewable life entries. For this, type max_life equals 24H0M0S and max_renewable_life equals 7D0H0M0S and save it by typing WQ. Now you have added max life and max renewable properties. Next, you will need to create the database which will store the keys for the Kerberos realm. For this, you will use the -s to create the stash file to store the master password. Type kdb5_util create -s and hit enter. Now you will be prompted to provide a password and re-enter a password to confirm. After creating the database, you will see how to edit the var/Kerberos/KRB5KDC/KADM5.ACL file to specify which principals have administrative access. First, type var/Kerberos/KRB5KDC/KADM5.ACL. Now you will have to define the realm. For this, edit admin@example.com to admin@test.com and save it by typing WQ. Now you will see how to create the first principal. You should create a principal which will have administrative privileges. So the first principal should exist before connecting to the server over the network. For this, type kadmin.local-q addprinc HDFS/admin. Now you will be prompted for a password for this principal. After providing the password, you will have to confirm the password. So now you can see the principal HDFS/admin@test.com has been created. Type service KRB5KDC start, and this will start the Kerberos related service, and then type service kadmin start. Now, type check config KRB5KDC on and check config kadmin on. So whenever the machine is ready, all these services should start working. Now type kadmin.local-p HDFS/admin, and you will be able to see the files inside the kadmin.local folder. Type list_principals, and you will be able to see the already existing principals. To add a principal, type add princ user1 and enter the password. Now type list_principals, and you will be able to locate your newly created principal, which is user1, and come out of KA-admin by typing in exit. You can test if your KDC is issuing tickets correctly. Any user who wants to connect to the Kerberos cluster has to provide a kinit command to get a token, and based on that token, the user can authenticate and get into the cluster if Kerberos is enabled. So, type kinit user1 and provide the password. Now you will have to check if kinit generated any tokens or not. For this, type klist-e and hit enter. You can see the token which has been generated for user 1. The token starts from September 15th and is valid till September 16th and can be renewed before September 22nd. Now, let us check if you can renew the ticket. For this, type kinit-R and hit enter. If you do not get any error, this means that your KDC is working fine. So the first two steps to enable Kerberos for your cluster, which is to set up a working KDC and configuring the KDC to have non-zero lifetime and renewal lifetime, have been completed. Now in the Enable Kerberos wizard page, you can check the boxes for the first two steps which have been completed. Now let us check if Kerberos client libraries have been installed on all the hosts. For this, you need to work on the Cloudera part. First, let us check the version of Java installed on the machine. For this, type java-version. Now type ls/usr/java, and you will be able to know the JDK version. As you can see, we have an old version of JDK. So to download the latest version of JDK, copy the link address from the website and type wget and paste the link address as shown on the screen. Now check if the latest JDK has been installed on the machine by typing ls. Type ls/usr/java, then ls/usr/java/jdk 1.7.0_67-Cloudera. Then type ls/usr/java/jdk 1.7.0_67-Cloudera/jre. Then ls/usr/java/jdk 1.7.0_67-Cloudera/jre/lib. And then ls/usr/java/jdk 1.7.0_67-Cloudera/jre/lib/security. Now you will be able to see local policy.jar file and US export policy.jar files. In every machine, you need to install KRB5 Workstation. First, start with installing on the first machine. For this, type su-ec2-user, then type sshM1. Now you will log in as root by typing sudo su, then cd. Next, type yum install krb5-workstation, pam_krb5, and press enter. As the krb5-workstation is already installed on the third machine, we have to install it only in the second machine. For this, type sue-ec2-user, then type sshM2. Now you need to log in again as root by typing in sudo su, and then type yum install krb5-workstation, pam_krb5. So now the packages are installed in all three machines. Next, you need to create a Kerberos principal and key tab file for Cloudera Manager Server. So type sudo su. Next, type cd, then type vi/etc/krb5.conf. Now in the #default_realm part, change #default_realm equals example.com to default_realm equals test.com. Similarly, in the realms, uncomment the sections as shown and change example.com to test.com. In the KDC section, instead of kerberos.example.com, change it to ip-10-0-0-221.us-west-2.compute.internal. Also, in the admin_server section, change kerberos.example.com to ip-10-0-0-west-2.compute.internal. Now, in the domain_realm part, uncomment as shown and make it as test.com, and then save it by typing in wq. Next, type kadmin-p HDFS/admin and hit Enter. When asked for a password, provide the admin password. Now, as you have to provide a principal for Cloudera SCM server, type in command add princ-randkey, Cloudera-scm/admin@test.com. Whenever you create a particular principal, the principal entry is in the database, and for that principal, you need to create a keytab file. For this, type kadmin-p HDFS/admin and hit Enter. Now, give the password and you will be able to log in as kadmin. Next, type xst-k cmf.keytab Cloudera-scm/admin@test.com, and you will be able to see all the entries for principals, and so a keytab file will be created. Once you have created a keytab file, you need to move that file to the Cloudera SCM server. For this, type mv-cmf.keytab/etc/Cloudera-scm-server. Type changeowner-R Cloudera-scm:/etc/etc/etc/cmf.keytab and hit Enter. Now type chmod 600/etc/Cloudera-scm-server/cmf.keytab to adjust the permissions on the Cloudera Manager server. Now you need to add the Cloudera Manager server principal to a text file named cmf.principal and store the file. For this, type vi/etc/Cloudera-scm-server/cmf.principal. And then type Cloudera-scm/admin@test.com. And then save it by typing wf. Now type chown-R Cloudera-scm-Cloudera-scm/etc/Cloudera-scm-server/cmf.principal. And then type chmod 600/etc/Cloudera-scm-server/cmf.principal. Now go to the Cloudera Manager and check the box for Yes, I have created a proper account for Cloudera Manager, and click Continue. In the KDC Information tab of Enable Kerberos for Cluster 1 page, change the Kerberos Security realm to test.com. In the Kerberos Server Host field, enter IP-10-0-0-221.us-west-2.compute.internal and click on Continue. Now in the KRB5 Configuration tab, check the box for Manage KRB5.conf through Cloudera Manager. After doing this, you will get further information about how to manage KRB5 conf through Cloudera Manager. Now click Continue. In the KDC Account Manager Credentials page, give HDFS/admin as the username and give the password and click Continue. After this, you will have successfully imported KDC Account Manager credentials. Now click Continue. In the Kerberos Principal page, keep the default values and click Continue. In the Configure Ports tab, check the box for Yes, I am ready to restart the cluster now, and click on Continue. So now you can see that Kerberos is enabled. It has completed all the steps, and Kerberos will start the service. In this demo, you have learned to enable Kerberos. In the third topic of this lesson, you will learn about securing cluster, configuration properties, and implementing service-level authorization. Service-level authorization is the initial authorization mechanism to ensure that clients connecting to a particular Hadoop service have the necessary pre-configured permissions and are authorized to access the given service. This is performed before performing other access control checks at file level on HDFS, or before checking permissions at job queue level. For example, a MapReduce cluster can use this mechanism to allow a configured list of users, groups, to submit jobs. It is disabled by default. To enable, edit $conf_dir/core-site.xml. The property is hadoop.security.authorization:true. Hadoop services and relevant configuration properties to enable service-level authorization include the following: security.client.protocol.acl. ACL for client protocol is used by user code via the distributed file system. Security.datanode.protocol.acl. ACL for data node protocol is used by data nodes to communicate with the name node. Security.nameNode.protocol.acl. ACL for name node protocol is the protocol used by the secondary name node to communicate with the name node. Security.inter.tracker.protocol.acl. ACL for inter-tracker protocol is used by the task trackers to communicate with the job tracker. Security.job.submission.protocol.acl. ACL for job submission protocol is used by job clients to communicate with the job tracker for job submission, querying job status, and so on. Security.refresh.policy.protocol.acl. ACL for refresh authorization policy protocol is used by the DFS admin and MR admin commands to refresh the security policy in effect. Access control list for each Hadoop service is defined in $conf_dir/Hadoop-policy.xml. It contains a list of users and groups separated by a space. Each list has values separated by commas. For example, user 1, user 2, user 3, group 1, group 2, group 3. A list of users includes only the users who are allowed to access the service. A list of groups includes a blank space followed by groups that have access to the service. All users who have access to the service are denoted by asterisks. If no value is specified with properties, then no one has access to the service. If the access control list is not defined for a service, the value of security.service.authorization.default.acl is applied. If security.service.authorization.default.acl is not defined, then asterisk is applied. To specify blocked access control list for a service, that is, to list the users and groups who are not authorized to access the service, suffix blocked at the end of property. For example, security.client.protocol.acl will be security.client.protocol.acl.blocked. Here is an example of a property. Property, name, security.job.submission.protocol.acl, close name, value, user 1, user 2, yarn grp, close value, close property. Access control lists are also applied to restrict access to data to approved entities only. ACLs are used to restrict access to HDFS. HDFS supports a permission model equivalent to traditional Unix permission. For each file or directory, permissions are managed for a set of 3 distinct user classes: owner, group, and others. There are 3 different permissions controlled for each user class: read, write, and execute. This works fine when file or directory permissions required for multiple users are the same. When the requirements of multiple users are different for the same set of files or directories, using permission bits like Unix is not possible. HDFS ACLs allow fine-grained file permissions for specific users or groups for data on HDFS. The following is used to implement ACLs: property, name, dfs.namenode.acls.enabled, close name, value, true, close value, close property. The property used for admins is dfs.cluster.administrators equals ACL-4-admins. The commands used to interact with ACLs are the following: HDFS-DFS-set FACL-M group group name R // HDFS-DFS get FACL / HDFS-DFS set FACL -M default group group name // ACLs can be enabled for yarn processing and used to control who can act as the administrator of the yarn cluster or submit job to yarn cluster and configured queues. The property is yarn.acl.enable equals true. To control access at queue level for administering the applications or jobs, or submitting applications or jobs, set properties in yarn-site.xml for capacity scheduler implementation. For fair scheduler implementation, set the properties ACL submit apps, ACL administer apps with the list of users, groups in allocations file. The list of users groups specifies the users or groups that have access to administer or submit jobs. Yarn.scheduler.capacity quename.support.acl_submit_applications. Yarn.scheduler.capacity quename.support.acl_administer_queue. We have discussed about queues in the lesson for computation frameworks 6 and 7. The following steps are used to grant permissions to users other than administrators on HDFS. They grant ownership of specific directories to specific users. This allows users other than administrators to write data to HDFS under specific owner directories using change owner or chown. They grant read, write, execute permissions to files, directories, to specific users on HDFS using change mode or chmod. When granting permissions to users on HDFS, the volume and count of data that they can write on HDFS is also considered. This can be controlled using quotas. To set count limit in a particular path, use setQuotaLimit. This allows users to write only a limited amount of data in a particular path on HDFS. Limit includes the count of files and directories. To set limitation on volume of data that can be written on HDFS in a particular path, use space quota. This can be megabyte, gigabyte, terabyte, and so on. using quotas to control amount of data written in HDFS. This demo explains how to control the amount of data written in HDFS using quotas. Let's open the terminal to set the quota in HDFS. The quotas are set in HDFS to specify the number of files and directories used and the amount of space used by the directories. There are various quota options available in HDFS. Use the command HDFS-DFS-admin to see the quota options, such as set quota, clear quota, set space quota, and clear space quota. Let's now set the quota in HDFS to restrict the amount of data written on it. Before that, let's understand the various items available in the cluster and user directory. To know the items available in the cluster, use the command HDFS-DFS-LS. You can now observe that the HDFS is the admin, and it is the only user that has access to write data on the directories. To know the items available in the user directory, use the command HDFS-DFS-LS/user. Here you can observe that there are various users such as Hive, Scoop, Uzi, and Hue that have access to write data on different directories in HDFS. Let's now create a directory for users, in HDFS using the command HDFS-DFS-mkdir/directory for users. To limit or control the number of files in the directories in HDFS, use the command HDFS-DFS-admin-set quota 2/directory for users. Here, the value 2 is the limit of allowed files, and directory for users is the name of the directory in which the quota is set to 2 files. Sometimes, you need to know the allowed limit of quota count in HDFS. For this, you can type the command HDFS-DFS-count q/directory path. Here, the directory name is directory for users. This command will give you the information on the available file limitation. In this example demo, you can observe that the number of files allowed is set as 2. The available counter is 1, and there is no set space limitations. Also, the number of directories created is 1, and currently there are no files available. Let's now understand the quotas with the help of an example. Let's create 2 text files, test100 and test101, using the command cat. Note that the available counter limit is 1. Let's write the text file test100 in directory for users in HDFS using the put command. You can check whether the text file test100 is written in the directory for users using the command HDFS-DFS-LS/directory for users. You can now observe that the text file test100 is written in the directory for users. If you write one more file, say test101, in the directory for users, the error message, "The namespace quota is exceeded," pops out as the available count limit is 1. So far, you have learned how to limit the number of files using the setQuota command. Let's now set the space quota in HDFS to restrict the amount of data written on it. The space quota is a hard limit on the number of bytes used by files in the tree rooted at the directory being configured. Let's create a new directory, Directory for Users 2, in HDFS using the command HDFS DFS -make directory / directory for users 2. To define space quotas on a directory, use the command dfs admin -set space quota. To set the volume of space quota, you need to represent the value in blocks. The formula should be the product of the number of blocks, block size, and replication factor. However, let's use the default volume. The default size of blocks in HDFS is 128 megabytes, and number of blocks is 3, so the volume will be 384 megabytes. Let's now check the space quota. You can check the count of space quota using the command HDFS DFS -count -cube / directory for users 2. Note that the available space of file 1 and file 2 is shown on the screen. Now let's write the text file test101 in directory for users 2 in HDFS using the put command. You can now compare the space utilized by the text file test101 with the available space. You can clear the set quota using the command HDFS DFS admin -clear quota / directory name. You can clear the set space quota using the command HDFS DFS admin -clear space quota / directory name. This concludes the demo on how to control the number of files and the size of data written in HDFS using quotas. Granting permission to users on HDFS. This demo explains how to grant access to various users to use HDFS. Let's open the terminal to grant access to specific users to use HDFS. The first step is to create a group. To create a group, use the command group add followed by group name. Let the group name be Hadoop 1. The second step is to add the new user in the created group. To add the user in a created group, use the command useradd -g Hadoop 1 user 1. Here, the user 1 is the name of the user, and Hadoop 1 is the name of the created group. You can also set a password for the newly added user using the command password. The third step is to create a directory. You can create a directory using the command HDFS DFS -make directory followed by the directory name. Let the directory name be user1dir. The last step is to change the owner of the directory recursively. You can change the owner of the directory recursively using the command HDFS DFS -chown -R followed by the username, group name, and directory name to which the user belongs to. Here, the username is user1, group name is Hadoop1, and directory name is user1 directory. Type HDFS DFS-LS to check the modifications made. You can now observe that the user1 has access to the HDFS. The user1 can now add, edit, or delete files in the user1 directory. Login as user1. Let's now add the file test1 in the directory, user1 directory, using the command shown on the screen. You can see that the test1 file is added successfully, and this implies that the access to use HDFS for the specific user, user1, is granted. The other way to grant access to use HDFS is by creating a common directory and granting access to it for all the users. To create a common directory for all the users, use the command HDFS DFS-MK directory /directory name. Let the directory name be common for all. Now grant access to this common directory for all the users. This can be done using the command HDFS DFS-change mode -R777 followed by the directory name. Capital R denotes the recursive change of the mode. In this demo, you have learned to provide access for all the users and for the specific users. This concludes the demo on how to grant access to various users to use HDFS. Enabling ACLs for YARN and HDFS. This demo explains how to handle Access Control List, or ACL, for YARN and HDFS. To enable ACL in YARN, perform the following steps. Click Cluster and click YARN Service. In YARN Service, click Configuration. Type ACL in the search box. Enable the checkbox yarn.acl.enable. This indicates whether users and groups specified in admin should be checked for authorization to perform admin operations. Type asterisk in the admin ACL box. Once this is done, enable the FAIR Scheduler if required. To enable FAIR Scheduler, type FAIR Scheduler in the search box, and you can see a list of suggestions. Select the required scheduler class and provide the allocations for different schedulers, such as QA, QB, and QC. However, in this sample demo, a specific ACLs that determines the service for submission and distribution has not been mentioned. To mention specific ACLs, you need to add the property shown on the screen. Once this is done, you can also enable the Capacity Scheduler if required. To enable Capacity Scheduler, type Capacity Scheduler in the search box, and you can see a list of suggestions. You can provide the required details. You can also add new allocations or properties by clicking the Add icon. The example property is shown on the screen. You can define the user who can access the service using the commands shown on the screen. You can replace the alpha with the queue name, username, or group name to whom you need to provide the access. You have now successfully enabled the ACLs for YARN service. Let's now enable ACLs for HDFS service. To enable ACLs in HDFS, perform the following steps. Click Cluster and click HDFS Service. In HDFS Service, click Configuration. Type ACL in the search box. Enable the checkbox hdfs.namenode.acls.enabled. Click Save Changes to save the modification. You have now successfully enabled the ACLs for HDFS service. This concludes the demo on how to enable Access Control List, or ACL, for YARN and HDFS.